Alright, YouTube, so let's continue to talk about gravitational wave. Okay, so as I said last time, gravitational wave is obtained by solving Einstein field equations in which the stress energy tensor is set to 0. Well, remember what it says, right? So, well, in the weak gravitational limit. So we can rewrite Einstein field's equation in this form, and here this is set to 0, right? This is defined as this. Is the weak limit of the gravitational field, where h is the trace. This is defined from here, the tensor from the approximation to the metric. So it's much less than 1, so it's very much flat, a little bit curved, but this is once again this is the special relativity. This is a wave equation. This is a three-dimensional wave equation. And anybody who studied quantum mechanics, well, quantum mechanics has the most famous wave equation. So we can solve this very easily. Right? It has this form where the k alpha, the right? Because what this because the special relativity tensor is nothing but it's just a shorthand. And when you take it again, you just get this. So this is equivalent to this. And now from here we can okay, so this is the constant, so just goes out. And this is nothing but this here. So this is ik alpha h bar alpha beta. So we can now see that if this will become I squared h, wait, this is mu. This is x mu, xk alpha. If alpha does not equal to mu, equals to 0, so this has to be mu. K mu so this can be said to be 0 if and only if k mu kv equal to 0. And this is equal to 0 if and only if and only if k. Well, this is, well, let's see what this is. We have mu here, so we can do the stress, we can do reason index. So this becomes kv, and this is known as tangent to the photon, to the equation of the photon. Okay, and we can write out this explicitly, right? This is well, we don't have yeah, this is k0. k2 squared plus k3 squared. This is equal to 0. Okay, so let's see what else is so this is null vector. Now what? Oh, okay, so in which case is this? To 0. So that means k alpha x alpha equal to 0. Kind of have to look at it. K alpha x alpha is the same as, so this is k0, k1, k2, k3, x1. So x1 is t, x1, y, z. So this is k0t plus k1x plus k2y plus k3z. So this is equal to 0. Need more papers. So let's call k1, k0 equals to w, omega, and so we can rewrite k as w, k1, k2, k. This can be rewritten as wk. This both face k. Okay. Now, if we define a photon in the direction of the null vector, we'll see how do we define photon traveling in the direction of the null vector? Well, this is its velocity. This is null vector, right? So what we do is we take its derivative. We find a curve that has it as its vector, and we do that by taking doing this. Wait, let's see. Taking the integral of this. And what do we get? We get a curve. We can get something like this. So w mu plus k1 mu plus some c constant K2 mu plus C2 K3 plus C3. Right. And just let's do a shorthand. Let's just say K mu times lambda plus C mu. Right. So that's so this is the position function of the photon traveling in the direction of the null vector, with the null vector being being tangent to the photon. Okay, so if we take the dirt, if we do this, if we take its conjugate, so I forgot it here. Then we get k mu lambda plus k mu c mu. Well, we know what this is. This, according to this, is 0. So this has to be k mu c mu. Okay. And we know this has to be constant because the c mu is constant. So now let's look at it. H this is constant if and only if this is true. And here we see this is also constant. So if we compare those equations, we see that photon has to travel with the gravitational field. And they have the same phase. And we can also from the nullity of k mu, which is equivalent to wk1 k. This might be carrying on too long. I don't want to take more than 15 minutes because then I can't upload this. So we can conclude from equals to 1, and so there's no dispersion.